Yeah, going after your advisor, no pressure at all. Uh, so a year and a half ago, I'm, I I joined Eric's group. I met him, and we spoke about ideas and overlapping interests. And like I was immediately on board. And while this discussion, he did promise me one thing. He showed pictures and all. He promised me that there's going to be one group meeting in Telluride. And believe it or not, that did influence my decision of joining Eric, joining this group. Um, I'm thankful for the organizers and the TLSRC staff for this opportunity. So I'll be talking about on noise-friendly quantum systems. So for both theorists and experimentalists in the audience, this should basically be unsettling, because what do we even mean that this quantum system is noise-friendly? But by the end of the talk, I'll hopefully be able to convince you that what we're working on really matters, and uh, that these quantum systems can indeed be noise-friendly. Awesome. So the way if this moves, yes. So the way I've organized this talk is I'll start by motivating and the idea and this motivation. I'll introduce the noise correlation model, talk about its dynamics, then talk about spontaneous synchronization, and finally talk about information theory that Eric spoke about a little bit. Some summary and take-home messages. What I'm really excited to talk about is I'll give you a glimpse of the future, the things that we're thinking about right now. And so most of this will be from these two papers that we worked on. Both of them are published. And in order to make up for some lost time, I will try to, what we have, our talks have like an overlap, and I'll try to go through those things fairly quickly. Great, let's talk about noise-induced synchronization entanglement. So if quantum mechanics is your bread and butter, you know that the way we do quantum mechanics is by typically assigning a state vector or a wave function to per state vector per isolated quantum system, and then we act on it by unitary operations, and we see this unitary evolution. But such quantum systems are not realistic quantum systems. Realistic quantum systems are ones that constantly interact with their environment. So what do? We want, as part of this analysis, we want to characterize these quantum systems that constantly interact with their environment. In fact, a strict demarcation of what the system is and what the environment is a fundamental limitation of the world we live in. There's no way to strictly demarcate between the system and environment, and that's why we see these dissipative effects with the environment. So it does not take very long to realize that the enemy in this whole story is this effect called, this phenomena called decoherence. So decoherence is this uncontrolled, non-unitary phenomena that leads to the complete destruction of a quantum state. I've listed some of the possible sources. So there can be thermal fluctuations in the environment, nuclear electronic vibrations within the system itself, and even in the most ideal case, temperature equals 0, we get some vacuum fluctuations that still will lead to decoherence. Decoherence is also tied to emergence of classicality that I will not be talking about in this talk. Now, one thing about decoherence is that decoherence is non-universal. Non-universal not in the sense that some systems can be preserved from decoherence, although by the end of the talk I will show that. But non-universal simply means here that decoherence is model or system dependent. So in order to give you like a sense of time scales, a typical two-level system in vacuum loses its quantum nature in about 10 to the minus 8 seconds, corresponding to spontaneous emission. A macroscopic object 10 to the minus 30 seconds. So if you compare this to the processing power of our brains, which is in the millisecond range, decoherence is practically instantaneous for us. Okay, so it's important that any system we study, we want this system to be robust against this effect. So we introduce a very simple but elegant idea. Again, we were talking about elegance. What if this noise is an ally of the system? Now, it is a simple but a very powerful idea. So how do we know this works? So I'm going to introduce 3 what I call metrics of success. The first thing is increased coherence time. So any coherences in our quantum system should be preserved for long time scales. The second one is if we can learn something fundamental, if we introduce this idea, if we can learn something fundamental about the system. And the last thing, which I really want to focus on in today's talk, and I will eventually get to it, is if we can monitor this information flow in our system that's interacting with the environment. And it's also like from 1 to 3 is increasing levels of abstraction, but what are we really interested right now is part 3. Okay, so again, so these are the things that I will sort of go very quickly over. So we introduce a system of, it can be coupled fermions or coupled bosons. So for a fermionic system, the first term simply sets the energy gap between the two levels. Second one corresponds to a transverse field, acts individually on qubits, also called the Rabi frequency. The third one is for the quantum information literature this is called the flip-flop operation. Essentially, this acts in the coherent subspace of the Hilbert space, also called the exchange coupling. For a bosonic system, the first two terms simply correspond to uncoupled harmonic oscillators. The third one represents exchange coupling. The first term corresponds to a destruction of quanta in 2, creation in 1, and the opposite process to make the Hamiltonian Hermitian. And of course, these system operators satisfy the fermionic or the bosonic algebra. Okay, now imagine, so the emphasis here is on the word local. So now imagine attaching 2 local noise channels to these 2 either qubits or harmonic oscillators, which represents an interaction with the environment. So we can take a product of some environmental noise given by E1 and E2, and we can take the product of that with some system canonical operator that I represent O here, because it can correspond to a Pauli operator or a creation and annihilation operator for bosons. These 2 noise terms can be packaged into what I call the vector stochastic differential equation, which I've written here. Eric spoke about that. It's called the Ornstein-Uhlenbeck stochastic differential equation. So the first term, A, the matrix gives the overall drift, which basically tells you how this noise is acting globally, so on this long time limit. B tells you what the perturbations are, and it corresponds to the diffusion. What we then also turn on is a correlation term between the environment given by this correlation matrix. What that means, any fluctuation in this environment is statistically correlated with the other one. So if this Wiener process decides to do something, this other Wiener process will also depend on that one. And what decides that is the noise correlation parameter that Eric introduced in his talk as well. Okay, so this noise correlation parameter has to be bounded between -1 and 1 because we want the noise correlation to be positive semi-definite so that it corresponds to a physical process. When psi goes to -1, it corresponds to anti-correlated environment. It simply means that if one of the Wiener processes, let's say one of the noise channel is pumping information into the system, the other one will take information out of the system. It's uncorrelated, basically means they're doing something randomly. If they're correlated, they're basically doing the same thing. So they can both pump information into the system or take information out of the system. I want to emphasize that for our model, this noise correlation parameter is the most important parameter of this whole analysis, because this will actually lead to the selection of modes that we want decoupled from the environment and from the noise. Great. So we can tie all of this together, and we can use we adopt the von Neumann style to represent the total system Hamiltonian, which is some unitary Hamiltonian and some interaction with this environment. Great. So we can pictorially describe what the system and the environment is. Okay. So our system evolves via the Liouville von Neumann master equation. Great. And the first term in this equation can be described by 2 parts. The first part corresponds to unitary evolution. The second part corresponds to this non-unitary dissipative part, which is given by this equation. Now, what the best thing about this equation is that it corresponds to a completely positive trace-preserving map. What that means is that eigenvalues of any arbitrary density matrix remain positive even after the evolution. So that's great. And it's trace preserving, which means the probabilities stay preserved. This is called the Gorini-Kosakovsky-Sudarshan-Lindblad master equation. I also want to emphasize that the word master equation here is kind of a misnomer. It's not like an action that you can derive all properties of your system from. It's just, you know, an equation that governs the evolution of the system. So I mean, when you hear master equation, you think of, you know, like a Dan Brown book or something, the master equation or something. It's not like that. Okay. Great. So the reason why Lindblad's name was attached to this was because he proved that the generator of any quantum channel satisfying the semigroup property, semigroup simply meaning that the inverse does not exist in the group, has this structure. So it's a completely positive trace preserving map, and the converse is also true. So for every physical operation, our dissipator is going to look like that, and the master equation is going to look like that. Even better, this equation preserves the linear structure. What that means is that a map M can take you from some initial density matrix to a final density matrix, and the generator of the map is what we call the Liouvillean superoperator. Great. Okay, so now we can construct our jump operators. So, okay, let me tell you why these are called jump operators. Because if you're familiar with Lindblad dynamics, even then, a very simple reason they're called jump operators because there's a high probability these local noise channels will do nothing, and a very small probability that they will extract some information from this system. That's it. So the total dissipator will obviously consist of both relaxation and excitation processes. And remember, I told you that we turn on this noise, this correlation between the fluctuations. So even though these jump operators, as I defined, they are defined locally, these fluctuations, of course, are correlated, and anything affecting system will also affect system 2, and therefore the total dissipator will consist of cross terms. Great. Now we can use the eigenvalues and vectors of this noise correlation matrix, and we get a very nice, neat structure of the dissipator. The dissipator simply breaks down into a symmetric and an antisymmetric part. So the jump operators for the jump operators can be given by this symmetric and an antisymmetric part. So these I will always come back to the structure of these jump operators as we see what happens when these modes decouple. So even better, for a bosonic system, we get a phase space like structure. Why? Because of two reasons. One we already talked about. So these jump operators are linear and canonical operators of the system and guarantee a CPTP evolution. The other great thing is that our Hamiltonian is at most quadratic in canonical operators. So any equation of motion, so H comma O commutator will be linear because it will only be a function of one single canonical operator, which means that we can define the whole evolution in terms of means and covariances, and the whole evolution generates the Gaussian map. Simply means if you start with the Gaussian state, you'll preserve the Gaussian nature of the state until the end. The covariance matrix has to be positive semi-definite and has to satisfy the Robertson-Schrodinger uncertainty relation, where omega is the symplectic form, which basically means that you have a dynamical matrix. In the dynamical matrix sandwiched between the symplectic form has to be preserved. So the Lindblad equation was in the Schrodinger picture. From the Schrodinger picture, we move to the Heisenberg picture, which means now operators are time dependent. We can calculate we can derive what we call the adjoint dissipator. And finally, if we package all the system canonical operators into a vector X, we see that our system evolves via these two final equations. You can see this equation is linear. Everything about the evolution, all the dynamics are stored in W, which is the dynamical matrix, and the covariances evolve via this Lyapunov equation, where F corresponds to the dissipative part. Great. So before we move on, we have to acknowledge this powerful observation by Brian May from Queen, or Christian 17th century polymath Christian Huygens. I show you these mechanical pendulum clocks as represented by these metronomes, and the mechanical coupling, which is this wooden block. And you see that with even in less than a minute, they will start synchronizing. So the immediate idea was that what if this behavior is also manifest in our quantum system? And without giving a lot of spoilers, that's absolutely true. For a bosonic system, if we calculate moment trajectories and extract the real part of these canonical operators, what we see is that for anti-correlated noise, we get a synchronized behavior. For uncorrelated noise, of course, the oscillators are unsynchronized, and for correlated noise, we get anti-synchronized synchronization behavior. And why I call this moment trajectory is because I just explained that we can label we can have quadratures in terms of system operators. So x can be a plus a dagger, and if you extract the real part, you'll see it basically corresponds to displacement from the mean position, which here is 0. And we see a similar behavior for the fermionic system as well. Great. Okay, so now everything, like I said, about this evolution can be understood by the dynamical matrix, by analyzing the spectrum of the dynamical matrix. So this equation gives the eigenvalues of the dynamical matrix. The first term corresponds to some global oscillations. The second term is an overall decay or damping. The square root controls the entire critical behavior of the system. Great. So for G equals 0, which basically means that we're removing the direct coupling we're removing the exchange coupling from the harmonic oscillators, we get spontaneous synchronization outside of this allowed regime. He was talking about this regime of allowed psi, and as soon as we hit the critical points, our oscillators will spontaneously synchronize. And this you can derive this very simply by setting this equal to 0, and you can immediately get delta over this range, this allowed range of the noise correlation parameter, and outside of this, our oscillator spontaneously synchronizes. Now, only for G equals 0, we have the exceptional points. Of course, this hints at any critical behavior hints at an exceptional point. Only for G equals 0, we get the exceptional point at the real axis. And coming back to the structure of jump operators, you can immediately see if psi goes to 1 or -1, either the antisymmetric or the symmetric mode becomes completely immune to dissipation and is completely undamped, while the other one experiences strong damping, which, as Eric also showed, is given in this plot. So, of course, an exceptional point hints at a dynamical phase transition in the system. So this is also called the spectral bifurcation. This happens where both these eigenvalues coalesce, essentially when the square root goes to 0. This is similar to a pitchfork bifurcation indicating PT symmetry breaking, but as we mentioned, not quite, because time reversal is broken by construction, and parity is broken because of this exchange, and we have correlated noise. Beyond the exceptional point, what happens is the square root becomes a complex number, and we instantly see that the real part splits and the imaginary part coalesces, which is indicative of a PT symmetry like behavior. It's not a pitchfork bifurcation, because after a pitchfork bifurcation you need to get 2 stable states. So it just looks like a pitchfork bifurcation, but it's not. But it is a dynamical phase transition nonetheless. So all of this can be traced back to the fluctuation dissipation theorem, which simply stated that there's a balance between an influx of energy from the environment and an efflux of energy back. Any disturbance to the balance, what happens is that it can transition the system into the symmetry broken regime, and the long time steady state gets locked in a non-equilibrium state. It can never decay back to the ground state. Great. And this locking, as I said, solely depends on the noise correlation parameter psi. That's why I said that this parameter is the most important parameter of the model. When we reintroduce the coupling, and Eric also showed that, our exceptional point shifts to the imaginary plane, and we can analytically continue our noise correlation parameter in the dynamical matrix, and we can think of adiabatically transitioning between different symmetry broken or unbroken regimes. But again, what does that even mean for material systems? So this is something that we should still figure out what that means. And for negative values of the coupling, the synchronization regime simply switch. So for anti-correlated noise becomes correlated noise, and vice versa. So we indeed know something. So coming back to this metric of success, we indeed know something fundamental about the system now. We know that our system, with this setup at least, goes through a dynamical phase transition, and spontaneous synchronization has some origin in this symmetry breaking property of the system. So that's nice. We learned something fundamental about the system. Now, we can quantify this phase locking value, essentially this synchronization behavior, by calculating the average phase difference between the two, between these canonical operators, by defining what we call the phase locking value in this time averaged sense for g equals 0. So when again we remove the coupling between the two oscillators, we see that beyond our critical value of the noise correlation parameter, the system rapidly synchronizes. And there's some oscillations in the allowed range, which just corresponds to the competition between gain and loss in this unsynchronized regime. And as soon as we reintroduce even the smallest values of a coupling, we see that we get spontaneous synchronization as soon as we're past these critical points. And you see these dips close to the critical points. These dips just tell you that the system wants to either synchronize or relax. There's a competition going on. But as you hit the critical value of the noise correlation parameter, the system rapidly synchronizes. So that's good. The other thing we study is the dependence on this overall decay, overall relaxation rate. And if you see that the spontaneous synchronization effect sort of fades away as the overall decay goes to 0, but as we increase gamma, we see that the synchronization effect returns. So now, in order to make some parallels with this, with symmetry breaking literature, the noise correlation parameter in our model serves as a tunable control parameter, and the phase locking value is the order parameter, which takes different values in different within the symmetry broken or the unbroken phase of the system. Great. So the point is, we can engineer a path in a way that becomes an ally, which basically means and this displays that coherences are preserved for longer time scales, because we're now locked in some non-equilibrium steady state. So for long times, both for bosonic and fermionic systems, the coherence in our quantum system is preserved. And that also gives us, the first metric of success, which is we do have increased coherence time in the system. Great. So now moving on to the third part, which is our current area of exploration. We're very excited about this. We want to monitor information flow in the system. We want to monitor what is exactly happening to the information flow as it interacts with this environment. So in order to tell you some more about that, I will have to introduce some literature. And a question that has been, lingering, and we really want to understand if this effect is intrinsically classical or quantum. If what exactly is happening there. Was it? Okay, so I'll introduce a quantity called mutual information. It represents the shared information between two subsystems A and B. This mutual information is given by this, of course, this formula. If rho here is a product state, then the mutual information goes to 0. If rho is a mixed state, then the mutual information is strictly positive. Mutual information contains information about the total correlations in the system. They can be both quantum and classical. And S is just the standard von Neumann entropy. Okay, so let's imagine initializing this system in some arbitrary initial state rho A, B. Given that rho A and B are correlated, again, so mutual information is positive, what we can do is we can perform a local measurement in subsystem B in order to know something about A, because they're correlated. Great. The classical correlation, sometimes also called the Holivo information, is given by this equation. The way to simply understand is that we have some reduced density matrix of subsystem A, and because we know something more about subsystem A by doing a local measurement in subsystem B, of course conditioned on a POVM, which is a positive operator valued measure, the entropy goes down of subsystem A, which basically means that we know something more about subsystem A. Now, if in order to make this quantity independent of the choice of POVM, we want to maximize this quantity of over this set of POVMs, over the set of all POVMs. And like I said, it just tells us how much more we know about A, given that we did some local measurement in B due to classical correlations between them, okay, not quantum correlation. So we can now filter out the true quantum correlations, because I told you that mutual information contains both classical and quantum information. So if we somehow take this classical information, classical correlation part out of total mutual information, what we're left with is the true quantum correlations in the system. And this is we calculate this by a quantity called discord. And as I said, we maximize over the set of POVMs, calculate the full whole Evo, and take it out from the total mutual information. Now you see I have an asterisk on maximize. I'm going to talk about that in a second. It is also worth to point out here right now is that correlations in quantum correlations have a nuanced structure and are directional, which in simple terms means that measurements in quantum mechanics are special. Therefore, discord is not symmetric. So you're going to get a different discord if you do some local measurement in B or if you do some local measurement in A. Just to keep in mind. Okay, so talking about this maximization process, this is a non-trivial process because we can essentially convert every POVM into another POVM by some arbitrary unitary transformation. Okay, so this maximization becomes a hard task, and there's like mathematicians essentially, it's a mathematical problem, and people are trying to understand how we can do this maximization. It's been understood for some systems, but for some POVMs, for some specific POVMs, but it doesn't have a general. People don't have a general idea. But we came up with a trick to do this. Okay, so the trick is we allow our density matrix to evolve. I gave you all the evolution equations, and then it goes to this long time steady state, and we by hand kill all coherences in the density matrix. So it represents a pseudo maximally classical density matrix. We calculate simply the total mutual information, and we take it out from the total mutual information of the original, the initial density matrix. And what this gives us is a lower bound on because we do this trick, it gives us a lower bound on discord. Okay. So I'm going to highlight some special cases here. The special case, at least for a fermionic and bosonic system, is when there's no direct coupling between the two. So either these qubits or bosons, harmonic oscillators, they can only talk to each other via this shared environment. As you see, as this noise correlation parameter goes away from 0, so towards anti-correlated or correlated noise, the first thing to notice is that mutual information becomes non-zero. Okay, so which means our system has both classical and quantum correlations. And now we do this trick, calculate the discord. For anti-correlated noise, we immediately see that the total mutual information, basically the dashed line corresponds to quantum discord. So for anti-correlated noise, any correlation that exists in these two quantum systems, in our system, is purely quantum mechanical. So pure quantum correlation. For correlated noise, at least we have non-zero discord, well, non-zero lower bound on the discord. So essentially what's happening is that classical noise, these systems talk to each other via classical noise, but it still leads to yes, 5 minutes. Okay. Oh, okay, then I should go a bit fast. Right. So we still don't know how information is moving in and out of these systems, but we do know that these correlations are intrinsically quantum. Good. So summary and take home messages: simply, coupled quantum systems. We show the dynamics of coupled quantum systems coupled to a dissipative correlated bath. The consequence, as I said, leads to a non-equilibrium phase lock synchronized steady state, depending solely on the noise correlation parameter. The underlying reason was a dynamical symmetry breaking. The novel result here, the most important thing is that this noise correlation parameter gives us allows us to select the modes that we want to be decoupled, and they live in this decoherence-free subspace of the total Hilbert space of states. And I showed this effect is quantum. Great. So now Eric talked to you about the whole statistical protection of modes. So I'm going to skip that, but I'm going to move on to a natural extension of this work is to large quantum systems, and we do that by identifying this noise network by some adjacency of the Hamiltonian given by a k regular graph. So adjacency matrix of a k regular graph, and we see that this noise correlation parameter is emergent in an infinite dimensional system, and the Q local Hamiltonian, if Q goes to infinity, what's going to happen if the system is all to all connected, this noise correlation parameter will go away. Great. So the way we do it is, imagine you put your system on a k equals 2 regular ring. So 10 sites, we have 10, let's say, harmonic oscillators. The green dots represent environments. And what you can do is you can try to densify. So you start with some sparse Hamiltonian, and you keep adding connections in the Hamiltonian, so make it more. So Q goes higher and higher. So make the Hamiltonian more dense, and you can understand how the system evolves. And if you do an eigenvalue analysis of this, you see that minimum eigenvalues of these k regular graphs, you see as a function of the noise correlation parameter, we have 0 eigenvalues and of course corresponding eigenvectors. And there's some analysis that we still have to do for what happens in the positive side. But negative noise correlation always gives us a 0 eigenvalue. These eigenvalues correspond to the modes that are eventually going to be protected from the environment. Okay, so what I'm extremely interested in is probing signatures of chaos in these non-Hermitian systems. The motivation was given by Larkin and Ovchivnikov when they were trying to understand superconductors. Essentially, in the semi-classical limit, a commutator goes to a Poisson bracket, giving you initial condition sensitivity, which is what the definition of chaos is. Going very fast, we want to calculate what we call the out of time ordered correlator. I'll give you a picture so that you understand what this is. But this is a correlation that can help us understand how quickly information scrambles in a quantum system. The average here is the thermal average. So an established fact is that in a Q local chaotic system, the out of time order correlator has this form, where lambda here now is the quantum Lyapunov exponent and VB is the quantum butterfly velocity. Great. And we can talk about the MSS bound. It's not important right now. But here's the pictorial thing. So imagine initializing your system in this particular configuration. You have a Heisenberg operator W at some site and another operator at some other site of the system. Initially, this has no support, so the commutator goes to 0. As this perturbation evolves with time, so we allow this Heisenberg operator to grow, the commutator becomes non-zero, and finally at t equals t star, which we call scrambling time, essentially what that means is that any initial perturbation of the system has completely spread to all degrees of freedom of the system. We have the maximum overlap and have the maximum value of the commutator, and this second operator is we insert the second operator. Well, it's there from the start, but now both of them share a support, so the value of the commutator is maximum. So you get an emergent light cone structure on how this information spreads in the system, and it gives you some, and we get some extremely remarkable result. I'll just take another 5 minutes. What we see is that for intermediate edges, so we start with a k regular ring and we keep adding edges. In the intermediate edges, the OTOC behaves normally. What that means is that in dissipative system, the OTOC has to decay because the information leaks out of the system into the environment. But for the protected system, for regular graphs, the OTOC does not decay. So this out of time order correlator in a dissipative system will not decay because I showed you that. So this non-decay process corresponds to these regular graphs up 10 sites, so 9 n-1 regular graphs. This OTOC will not decay. This was by the way for anti-correlated noise. For uncorrelated noise, of course, the OTOC is essentially a delta-like behavior. It decays immediately. And same for correlated noise. For intermediate graphs, the OTOC decays but remains protected. Now the OTOC, using the OTOC, we can calculate what's called the scrambling time. And as you can see, as you densify the graph, for both intermediate graphs and k regular graphs, the scrambling time increases. So again, coherences stay preserved for longer times. For anti-correlated noise, for uncorrelated noise, it just remains the same. It doesn't change. For Correlated noise, there's a jump in the end. I can talk to you about why this jump happens, but I think I don't have time right now. Okay, and then the next thing we're absolutely interested in is to probe dissipative signatures of chaos in dissipative systems, and we have these two guiding conjectures. I highly recommend reading this paper by Prozan and collaborators, and they essentially tell us that for uncorrelated energy levels in the Hamiltonian, so let lambda be some spectrum of a non-Hermitian Hamiltonian. For uncorrelated levels, we get a Poisson distribution, and for chaotic systems, we get level repulsion spreading throughout the system. This is like a signature of chaos, and I can talk more about that privately. Great. So real world impact, essentially, the broad impact is to build scalable quantum technology, understand light harvesting systems, and this is an AI generated image that we really like of a molecule wearing headphones. Essentially, our model works like the mechanism is very similar to a noise cancellation headphone. And the third part is where we're basically interested even probing signatures of chaos experimentally. So I'm more than happy to talk about that. So I'm not an experimentalist, but you can have a Maxwell daemon kind of setup to understand systems interacting with their environments. In fact, one last thing I'm going to mention this paper that I think Eric, Andre, and collaborators came up 5 years ago or something, which they saw a similar effect. They've seen a similar noise-induced synchronization effect, but they also talk more about the experimental side of things. So if you're interested, please go ahead and read that. Okay, I'm going to flash some key references. That's me and Eric. That's how I'm going to summarize our relationship. That's what it is. So, well, I'm really grateful to have Eric as my advisor. I mean, his contribution has been invaluable to nurture me as a physicist, from advocating for science in DC to public outreach, showing people how synchronization works, and to discussing wild ideas at Los Alamos. You see what the common denominator is? Or an intoxicant in all the three pictures. There's an intoxicant everywhere. Also, Eric gave a great interview, and you should check that out. I'm going to share one small thing before I close. So I had come back from a school, and I'd learned so many new things, and I was like, hey Eric, we should think about this, and I was learning about representation theory and probability flows and manifolds, and he becomes really serious, and he says, no, pick one of your Hamiltonian's knobs and tell me what the physical thing it corresponds to in the lab, and how would we detect it. And then I was like, oh man, I mean, okay, that's his philosophy. Goes to the board, picks up a marker, starts talking about representation theory and probability flow and manifolds completely. But I mean, the idea is that he's grounded by. He was talking about this. The philosophy that he follows is that he's grounded by experiments, and he wants to collaborate with experiments, and also loves to work on the theoretical and abstract side of things. So I think happy early birthday. Thank you everyone for your attention. I have a podcast if you want to check out. Thank you. Question.